So we're going to start with section 10.3 on what are called alternating series. So here's an introductory paragraph from the textbook. So I'm just going to read a little bit of it. So earlier on, we were studying infinite series with positive terms. And obviously, that's a very important area of study. But then there are many interesting series where the terms have mixed signs. For example, in this series, two terms are added, then two are subtracted, then two are added, and so on. Now, this may look interesting, but then there is no end to these kind of patterns. So we need to restrict our attention. So first we look at the simplest sign pattern, and it turns out that it is also the most important. So we are going to consider what are called alternating series in which the signs strictly alternate. So for example, here is a series summing from 1 to infinity, negative 1 to the power k plus 1 over k. So let's put k equals 1. If you put k equals 1, you get negative 1 to the power 2. So that's plus 1 divided by 1. So you get 1. Then k is 2. So you get k plus 1 becomes 3. So negative 1 to the power 3 is negative 1. So you get a negative sign and then 1 over 2. Then plus 1/3 minus 1/4 and so on. So this factor that you have in front, which is negative 1 to the power k plus 1, or sometimes only negative 1 to the power k, gives you this pattern of alternate signs. So in this section, we will study the convergence of such alternating series. So from now onwards, when I write AS, it stands for alternating series. And by the way, this particular series, if they are all positive, for example, if it was just this, which you have seen many times, it's 1 plus half plus 1/3 and so on. It had a name, harmonic series. But if you have the alternating one, like this one that we just saw, it's called alternating harmonic series. It's a very important series and it shows some very interesting properties. So, first, to have some good intuitive idea about what alternating series and how they behave. So, the best way to understand what is the difference about behavior of such series is by these examples. So, please pay close attention and try to see or develop some intuition here. So, I'm going to look at three cases. First case. So, you have a series like this. So, notice that all the terms are added. There is no alternating going on. So if you have 2 raised to the power k over k, it has terms like these. It's pretty easy to check that this one diverges. Actually, you can look back, you can test it by ratio test. So you will see that it diverges. Now, if I take the alternating version of it, in other words, I make the signs alternate, which means one term subtracts, then add, then subtract, and so on, then we can show, you will see how very soon, that this series still diverges. So the series where there's no alternating going on diverges, and when it alternates, it still diverges. Okay, not surprising. Now look at the second case. Now here we have the famous series, our harmonic series, and we obviously know very well that it diverges. So it's adding up terms, and if you keep adding them up, it happens to diverge. But interestingly, if you have alternating signs, so that means you subtract and then you add, then you subtract, it turns out that this series converges. So the alternating version of this particular series converges. Now let's look at case 3. So now you have the good old 2 series. So 1 over k squared, so you get 1 plus 1/4 plus 1/9 plus 1/16 and so on. Now we know very well that this one converges. Now when you take the alternating version of it, same series, but now you alternate. So you subtract and then you add and so on. This alternating 2 series also converges. So what we noticed here is if the absolute version of the series diverges, like for example case 1 or case 2 above, the alternating version of it could converge. So that was case 2. But that is not always so, because as you saw in case 1, the alternating version diverged. Now, if the absolute version of a series converges, this we are talking about case 3, then the alternating version would always converge. This is a theorem which you will see a little later, which says if the absolute series, I'm talking about this case, so if you have the absolute version of it, if it converges, then the alternating version will definitely converge. And if you think about it intuitively, it makes perfect sense, because if the absolute version converges, that means you are adding all these terms, and despite adding all the terms, you still end up converging. That means it turns out that the sum is some nice number. Let's say, well, we know in this case it's pi square over 6. Then if you alternate them, that means you are subtracting every other one, then definitely this sum that you're going to get is going to be less than this. So this will be less than pi square over 6. So therefore this one will also converge. So it makes pretty good intuitive sense. So the point here is that the absolute series version has greater requirement. You have more demand on it for it to converge. In other words, it is easier for an alternating series to converge. So hence we cannot use the convergence tests that we have learned till now. So we cannot use all those tests that we had, because they are much stronger situation. Alternating series converge more easily. So for that we have what is called the alternating series test. So AST stands for alternating series test. So we use this only for alternating series. Never use it for regular series, only if they are alternating. Okay, so we are given this alternating series, and it converges if the following two conditions are met. The first one is saying the terms of the series are non-increasing in magnitude. In other words, the terms are monotonically decreasing, actually non-increasing. For k greater than some index n, that means after few terms it starts going down. And the second condition is that limit of ak is 0. So first thing to notice is we are looking at ak. as a sequence here. Second thing, so this is the first thing. The second thing we notice is that AK is the term without the negative 1 raised to the power k sign. So you leave the alternating part and just pick the non-alternating portion to study it. So few notes. We will obviously apply to alternating series. Do not apply this for other types of series. A lot of students make a mistake of using this to test other kind of series. The second thing is that I will interchange the order of the test given in the theorem above. In other words, I'll just interchange the order. It's more common that way instead of this order. So let's apply the alternating series test to check the convergence of obviously the most popular one, and that is the alternating harmonic series. So this is the series that we are studying. So the first thing to do always with alternating series is to pick out the AK. Now remember, AK is the term without the alternating sign. That means in this case AK is 1 over K. Now we are going to check each of these two tests. So I'm going to do this one first, and then I'll work on this one. So T1 is the first test. So what that means is I'm going to check if limit k going to infinity AK is equal to 0. Is it? Okay, so let's check. So let's find this, which is obviously trivial in this case. Limit k going to infinity, AK is 1 over k, and that limit is 0. So yes, so it works out. Now let's go to the second test. So now what we have to do is check if AK plus 1 is less than equal to AK. That means the term decreases, or at least does not increase, it's less than equal to the previous term. So what is AK plus 1? It's 1 over k plus 1. And what is AK? It's 1 over k. So the question is, 1 over k plus 1 is less than equal to 1 over k? Is it? So let's just cross multiply, and so we're going to get k less than equal to k plus 1. I'm just taking this here and this one there. So you can cancel k and you get 0 is less than equal to 1. Is that true? Yes. So therefore T2 is also true. So when we have both tests true, so this one was true and this one is true, so we can conclude that the given alternating series converges. Remember, it's the alternating series that converges. That's why we were using the alternating series test. Okay, let's continue with the next example. So here, always make it a rule to pick out AK first. So let me write down AK. So AK would be k over k squared minus 1. So just pick out this component. Leave this behind because we know it is alternating. So test 1. Check if limit k going to infinity AK is 0. Is it? Well, let's take the limit. So how do we check? Well, we divide numerator and denominator by k squared. So that gives me 1 over k divided by 1 minus 1 over k squared. Now take the k going to infinity. So this numerator is 0, denominator is 1 minus 0, so that is obviously 0. So that's good. Yes. So test 1 is true. Now let's go and try out test 2. So in test 2, we want to check that ak plus 1 is going to be less than equal to ak. Is that so? Okay, so what's ak plus 1? So wherever you see k, you're going to write k plus 1. So k plus 1 over k plus 1 square minus 1 less than equal to ak. That would be k over k squared minus 1. So now we can cross multiply. So you get k plus 1 times k squared minus 1. Is it less than k times so let's FOIL and clean it up. So if I FOIL this, what would I get? K cube minus k plus k squared minus 1. And on this side I have k times, so let's square this, k squared plus 2k plus 1 minus 1. So these two cancel, and I have, now let's multiply by k. I'll get k cubed minus 2k squared. Okay, so bring everything on one side. So this and this cancels. If I bring this term on this side, I'm going to get minus k minus minus k this is plus 2k squared. This term was plus 2k squared, so when it comes on this side, I'm left with minus k squared and then minus 1 less than equal to 0. So that means negative k plus k squared plus 1 less than 0. Is it? Well, this is always positive. K squared plus 1, all these three terms are positive. And then you have a minus sign in front. So overall, this is a negative number. So is this less than equal to 0? Yes, sure. So therefore, T2 test 2 is true. So we have test 1 and test 2 both are true. So therefore, the alternating series converges. But you notice that this was quite a bit of algebra and time involved. So we have a very nice result which makes it much faster and easier. So let me explain what this result is. So let AK be a sequence. So this comes from the previous sections of sequence of positive terms. And let Fk be A of k for all k. So f of k is like our generating function that we had earlier. So this is our generating function. When we were studying sequences, we saw that. Then AK is monotonically non-increasing. That means this is what we require if the derivative of f is less than equal to 0 for all x greater than n. So that means basically the derivative is negative or less than equal to 0 after some value of x, at least after some value of x. So if we were suppose trying it on this particular problem, this particular question, so my ak was k over k squared minus 1. So therefore my function would have been x over x squared minus 1. Now I would use quotient rule to find the derivative. So my f prime of x would be derivative of x, so that is 1 times the denominator, which is x squared minus 1, minus the numerator, which is x, times the derivative of the denominator, which is 2x, divided by square of the denominator. So x squared minus 1 squared. So the numerator is very simply x squared minus 1 minus 2x squared, and the denominator is always a positive number because notice it is squared. So we really don't care for the denominator anymore. So let's just look at the numerator. So what is this? This is minus 1 minus x squared. Now this is obviously always less than equal to 0. This is negative 1 minus a square quantity is always going to be negative. So using this result, we have shown that ak plus 1 is less than equal to ak. So test 2 can be done much faster and easier manner using this result.